Hello, I am Nathanael Gunawan, and I am currently a senior in Western Regional High School, and this is my project on a novel magnetic train using a dipole line track system. Why is maglev technology a potential solution to a growing transportation problem? The worldwide urban population is rapidly expanding, and it constantly demands faster and highly efficient forms of transportation. Currently, we have conventional trains and airplanes, but there is a huge speed gap between the two. For example, the maximum speed of the conventional train is about 300 kilometers per hour, while planes can achieve much higher speeds at 925 kilometers per hour. This speed gap causes a convenience disparity where certain distances are inconvenient for either forms of transportation. For example, the distance between New York City and Washington, D.C. is approximately 370 kilometers. With current American train systems, it would take approximately 3 hours to complete the trip. With a commercial plane, the trip would be around an hour. However, the process for a plane ride, considering the security, baggage check-ins, boarding, and overall waiting, is inconvenient for a relatively medium-sized distance. Maglev trains are an alternate form of transportation that can bridge the speed gap. The Japanese model, the SC Maglev, achieves a perfect average between the two speeds, 600 kilometers per hour. The reason maglev technology has the capability to consistently achieve high speeds in the range of 500 to 600 kilometers per hour is mainly due to the unique levitation aspect. This means during the operation, the train is not in contact with the track, which removes any resistance from surface friction a conventional train would experience. With this top speed, the SC maglev could make the DC to New York City trip in approximately an hour as well. In a sense, you get the convenient process to board a train with the trip time and speed of a plane. Unfortunately, there are several issues with the current maglev system that prevent its global implementation, so my motivation in this project is to find a solution for this. Current technology. There are two maglev technologies in use, the EMS and the EDS. The EMS uses electromagnetic suspension, which are the attractive forces between electromagnets and ferromagnets with negative feedback, and the EDS uses electrodynamic suspension, which uses the repulsive force between superconductor magnets and metal loops. Both have several advantages, such as high speed, reliability, and efficient maintenance. Unfortunately, the problem is that they both exhibit disadvantages for levitation, such as complex feedback systems, costly cryogenic liquids, and an inability to levitate at low speeds. My hypothesis is that using diamagnetic levitation, I can create a maglev system that can levitate perpetually at all speeds. This alternative system can potentially solve problems of both the EMS and the EDS concerning levitation, while also increasing efficiency for a potential maglev system. Creating the maglev based on diamagnetic levitation. So how I made my maglev. Maglevs have three aspects: levitation, guidance, and propulsion, and in my project I only focus on levitation and guidance. When constructing my maglev, I only had two components responsible for levitation: dipole line magnets and graphite rods. Dipole line magnets are magnets with magnetization along the diameter in comparison to a standard cylindrical magnet where the magnetic field goes through both ends. And graphite rods, which are a diamagnetic material, which means that the magnetization is opposite in direction of the applied magnetic field, which results in a repulsive force. Using three parallel evenly spaced dipole magnets, I can have two graphite rods individually levitate between two magnets. After attaching a styrofoam train body, I have a successful maglev prototype that can levitate perpetually. Tests I performed. I performed three tests on my maglev. The critical gap test, where I designed and 3D printed multiple fixtures of increased gaps and tested each gap to find when the graphite drops. I found that the critical gap was at 1.8 millimeters, which is about 56% of the magnet's radius of 3.2 millimeters. The lateral stability test. I set up an experiment using an inclined plane and increased the angle until the train dropped. I found the angle to be 16.9 degrees, and after introducing a banking angle between the magnets, I was able to increase the inclination angle to 18.5 degrees. And then the load bearing capacity test, I constructed an empty maglev frame, put it in a track, and put square pieces of paper on the frame until it dropped. The load bearing capacity of the system, including the paper and frame, was 82.3 grams, which is about 97% of the mass of the base graphite rods, which was about 85 grams. Scaling up my prototype. So I calculated the total load per unit area of both my prototype and the SC maglev in Japan. Mine was about 0.4 kilograms per meter squared, while the total load bearing capacity of a real maglev is about 345 kilograms per meter squared. So the SC maglev has a total load bearing capacity about 860 times larger than my prototype, which is fairly reasonable considering the material and the size of my prototype. I can improve the total load bearing capacity of my prototype by replacing the graphite rods with superconductors, and since it has a magnetic susceptibility 5,000 times larger than graphite, my prototype can theoretically have a total load bearing capacity of 2,000 kilograms per meter squared, which is almost 6 times larger than the SC maglev. So summary and future work. I constructed a longer track to test if the train could actually function. And in this table, I summarized the comparison between the EMS, the EDS, and the TDL systems. The red means unfavorable and the green means favorable. And as you can see, the TDL is able to successfully overcome the issues of both the EDS and the EMS. The TDL system can also be extended to 4 magnets or more. I've created a newer concept to account for a propulsion method and for better stability as well. This maglev system can also be utilized in many proposed hyperloop systems around the world. And that's it. Thank you for watching, and hopefully in the future you'll be riding a maglev on a dipole line track system.